Welcome back. This is Christy Lutz, and I'm here to talk today about pressure. So, pressure is force per unit area, and it's measured using a pressure gauge. And so that measured value is going to be something we're going to call a gauge pressure. So that is going to be the force applied per unit area, and it's not going to sense what that atmospheric pressure is surrounding you and this surface. All surfaces on Earth are also going to experience atmospheric pressure. Okay, we're going to designate that P atmospheric, so P with a subscript ATM. Okay, and this is going to vary with location, but we're going to set it as a standard typical value of 101.3 kilopascals or 14.7 psi. Now, psi, if you haven't really done much with pressure yet, is a pound force per inch squared. So it's that force per unit area very clearly when you see it that way, but when you see it as psi, it looks very confusing. Now, all the calculations we're going to do are going to always be done in absolute pressure. So absolute pressure takes that gauge pressure, that force per unit area that you experience, and adds to it the atmospheric pressure that the air is pushing on around you. And that sum will be the absolute pressure. We're going to designate that PABS. Now, every calculation that you ever do needs to be in absolute pressure unless you are told explicitly that gauge is okay to use. It's very unusual. So here's a problem that's out of the textbook. A diving suit has a little window for people to look out of. Okay, it's about 65 square centimeters. And you're wanting to keep the pressure inside the suit at 1 atmosphere, right? You're in there, so you want that to be 1 atmosphere. So what force would you need to have on the window if you wanted to dive to a depth of 150 meters? Now, usually you're doing this in water. We'll take the specific gravity to be salt water, 1.05-ish. It varies a lot, but that's a good typical value. Okay? How are we going to solve this problem? So we've got the 1 atmosphere we want on the inside of the window pushing out. We're going to have the weight of the water, okay, the force, okay, so that's going to be the mass of the water times divided by the area that it's in. Okay, so if I have something of height H and area A that's pushing against something of area A, that pressure is going to be just that height times the density. Okay, to turn it into a weight, I need to then say times G. So that's going to get me the force, but then up above the water, there's the atmosphere still pushing down. So my solution therefore is going to be that I'm going to have to take that atmospheric pressure plus the rho GH, that's the weight of the water above me. And then I need to subtract off the 1 atmosphere pushing back. So the pressure difference that I'm needing is going to be, well, it looks like it would be real simple, right? 1 atmosphere here, 1 atmosphere here, so it's just rho GH. But I have to play the unit conversion game. Okay, G sub C is going to show up, 1 Newton per kilogram meter second squared. And so, based on this, I'm going to be able to calculate a delta P. The force is pressure times area, right? Pressure is force per unit area, so force is pressure times area. So 154 newtons per square centimeter times my 65 square centimeters. And I end up with 1 times 10 to the 4th newtons, or 2,250 pounds force. Manometers are another topic that they discuss in the textbook. This is one of the ways that pressure might be measured. It's with a manometer. A manometer is essentially a bent tube that's filled with a liquid. The two sides are exposed to different pressures. Okay. The way that a manometer works is that at a particular height within the liquid, the pressure will be the same for all the molecules of that liquid. So whether it's on the right side of the tube or on the left side of the tube. So if you look at this height right here, this pressure is going to be exactly the same as this pressure. This pressure is the same as that pressure. Unfortunately, up here I can't use that rule because I don't have anything corresponding on this side. So the way we use this is, if I know the pressure on one of the two sides, the high pressure will push further on the fluid, and I'll have this height difference here. This height difference, rho GH, is going to be the way that I can define the pressure difference between my low and my high. I then could turn that into an absolute pressure if I knew any one of these with any certainty. So again, look through the book. Again, I assume that you've seen pressures in other courses, and you will in many other courses. So this was a very brief overview. Next lecture is going to be on temperature.